Okay, so let's get started. So yes, as Angela mentioned, we are going to do a little bit more hands-off session that we wanted to do. So I will be showing how to deal with the data products that we have, because we have a lot of data products. And with Agile, we are kind of in a unique position that we are using so many different softwares that the data model that we have, like the overall underlying data model of all of the data that we have, is partly inherited from running Egg. The Galaxy catalog that we have is partly inherited from doing image simulations with ImSim. These are the raw images that we have, and it's partly inherited from the LST science pipelines. And the point of the notebooks that we have compiled is more or less tried to tie it all together. Because for the LST science pipelines and for the data previews, we don't want to try to outdo the documentation that's already available. So if you want to know how to play around with the object tables in the data previews, we are always suggesting to go to the documentation of the data previews. For data preview 0, data preview 1, and follow that documentation, because we are using the official LST science pipeline, so everything should be up to the data model. So that being said, I will just go through what we have in a little bit more detail, the notebooks that we have demonstrated the data. And the idea that we have in mind is that we host all the data in Naples. And then at the moment, the way to connect to Naples is through Visual Studio Code. So this is, at the moment, I'm running this here, and then it's connected through SSH to Naples, where I have all the notebooks and all the data is available. And as I mentioned yesterday, it's about 3 terabytes of data total. And then just the catalogs is about 130 gigabytes. And just the deep coded images is about 30 gigabytes on top of that. So it's a little bit more manageable. But the full data set, including everything, is 3 terabytes. So this is just an introduction of what we have. So the 1 square degree in Cosmos. Limits about the truth catalog, so you know that we are missing the local universe, so we go from Redshift 0.2 to 5.5, and then we have a complete Galaxy catalog down to 10 to 8.5. This is of course empirically derived as well, so we are not, the Cosmos stellar mass function, for example, is not complete to Redshift 5 and low stellar mass of 8.5, so there's always going to be extrapolations in the catalogs. We have the 1,441 visits that we have simulated, and then a description of the LST science pipelines, and then a note towards the data model of data preview 0.2. You know that they changed the data model for the data preview 1, so some of the things, the names of the data products have changed between data preview 0 and data preview 1. So we are more closer to the data preview 0. So for the hands-on stuff, I will just demonstrate. I will not be going through the code line by line. I will just demonstrate the ideas that we have in place. So how to access the catalog and do the things that you want to do. So the basic gist of it is that we have a master database in place. This is a SQLite 3 database, and we have put all of the catalogs there. For example, our first source photometry catalog is 330 million rows. So this was at the limit of trying to put in everything into a FITS file that we can share, and we came up with the solution that we're going to mimic the data preview by creating a database that we just put all the catalogs into. And so here is the Python block of just asking the 10 first rows from the master object table that we have. So you connect to the database, and then you use pandas to just do a SQL query. And this is the flavor of SQL that they're using in SQLite 3. So you're asking for the 10 first rows with the limit command. And this is the object table, the same object table that they have in the data previews, and this is the one from the deep coded images. And it's a lot of columns, I think it's said right here. So this is 1,185 columns, because you have the fluxes in all the different 6 bands. You have the fluxes in different apertures, Coron fluxes, PSF fluxes, C model fluxes, and it quickly adds up to a lot of columns. So this is usually when you would like to work with this table, you would just select the columns that you want. But everything is there that is in the data previews as well. So this is kind of like the master catalog from the deepest exposures that we have. So as I mentioned yesterday, we are mimicking the data preview. So we put these different tables into the master database. So you have information about the visits. You have information about the individual CCDs. We have 21 CCDs. The LSST CAM has 189. And this table is the one, the object catalog that we have. And then you take the object, you go back to the single visit image, you do forced photometry on the location of objects. So this is the largest catalog that we have. And then this is what we don't have in the real life. So this is the underlying truth catalog. So this is where we would go for the, for example, the galaxy properties, stellar masses, redshift, star formation rates. The AGM properties are there, accretion rates, fluxes, everything that is on the, let's say, in the 24 square degree truth catalog is stored there. And well, maybe I can show. So this is from the slide yesterday. So this is sort of the columns that we are storing in the truth catalog. Some of it is applicable to AGN, some of it is applicable to galaxies, and some of it is applicable to stars. So for example, these 2 columns right here at the bottom of the page is the proper motion for stars that we are inputting in the simulation. And then, for example, EB minus V, this is the reddening law that we apply on top of the AGN. And then we are simulating a whole list of fluxes, not just the 6 bands in the LSST, but anything that we thought that would be useful later on when we are doing validation of the truth catalog and whatnot. So the truth catalog is in principle even more complete than what we are simulating in the images, just because we try to make it as useful as possible. And yes, these 2 columns give you which galaxies are labeled as AGN, because the definition of an AGN that we have in the simulation is that we set a limit on the accretion rate, which is roughly 1% of Eddington, and then we are calling anything that is above this accretion rate an AGN. So then we have this flag in the truth catalog also saying which galaxies are actually deemed as AGN. Okay, jumping back to here. So the truth catalog is there, and then this useful table is the matches between the truth catalog and the object table. So for each object that is detected in the images, you go back to the truth catalog and try to find the best matching counterpart using the positions and the fluxes. So this means that you can then go to the object table, and then you can ask the matches in the truth catalog, what is the type of this object. So is the galaxy, is it AGN type 1, AGN type 2, is the star? And that is very useful, because then you can also take the object table, you go through the matches from the truth table, and then you ask for example, stellar mass or redshift or star formation rate of this set of Ugritz measurement that you have in the object table. And this is also what we are using to do the flux versus flux. So we are asking the truth catalog for the truth flux, and then we are asking the object table for the measured flux. Okay, so in this particular notebook, it's just a couple of different queries showing you how you can do things with the table. So for example, you can select these particular columns from the object table or the forced photometry table. So this gives you the array deck positions of the objects, and then it gives you the forced photometry PSF flux and what was the band that was responsible for that measurement. And it's just a couple of lines of SQL, and then you get already a table that you can use, for example, for the force photometric light curves. In another example, so this is again matching two tables together. So we're using the object table, we're using the matches truth. We join them together, and then we're asking about the truth type of each of the detection in the object table. And truth type 2 corresponds to galaxy. So the top 10 rows of the object table, just galaxies. Finally, this is joining together the force source table and the CCD visit table. So we take the force photometry, and then we attach each data point in the force photometry table the time of observation, because as in the data preview 0, those who completed the tutorials, we need to use two tables to actually get the flux and the date of the observation. So okay, that's the bare minimum that you can do with the catalogs, with the data model that we have. I will then we can also poll if there is something specific that people want to see. I can be more specific about, for example, we can go to the images to show how to access the images. We can go to the SCDs. We can go to the light curves if there's any preferences. Okay, so by popular vote. So this is the notebook demonstrating how do you get the force photometry light curve for an object that you want, and then also how do you get the truth light curve, because we're storing for each AGN, we're also storing the true light curve, so you can do a comparison between the measured and the truth. And let me just verify that it's run, because
the difference is in the error and the host galaxy photometry, which is added, right?
The what?
From the truth. The truth is the input light curves of the AGN, and
yes, and then you have the host.
what you measure, you have the host and the noise on top and all the process.
Yes, and this is so I think it would be a useful investigation. How do you actually retrieve the total flux correctly? Because in the force source tables, this is part of the data model that there is only the PSF flux. So in the force source table, you don't have any measurements of the flux other than the PSF flux. So yes. So what we have done is a conservative approach. So usually we would just ask for the point-like sources where we know that the PSF flux is the correct one to use. So we are neglecting the local AGN that have a host galaxy contamination. Okay, I will not again. I will not run through the code. I will just go to the results. So this is I'm selecting in this notebook just basically 5 AGN that are AGN dominated from the. Well, maybe that part I should show. What is the sample selection? So again, this is another SQL query. Not going through it line by line. The important point is that we are selecting sources which are completely dominated by the AGN at the level of the truth catalog, so that the point flux, so this is the flux of the AGN, is 99% of the total flux. So this is partly for demonstration purpose, because here we were also using this particular notebook for validation, internal validation, looking at the light curves and seeing that everything works and what kind of errors we are getting just by nature of the science pipelines. And yes, this was the other point, that we are selecting objects that are not extended. So we are using this ref extendedness, which is the extendedness measured in the reference band. which I think is usually the I band, but it could be any of the 6 LSST bands. Okay, so it's a few Python cells of code, but in principle this is then the result that you have. So in this, it's the 6 LSST light curves. You have the truth light curve, which we are simulating to 10-year accuracy over the time span of 10 years. And then we have for each day of observation, we have 1 data point. So that is the truth light curve that you can see here in the 6 different bands. Why is the normalization different? Well, the SCD of the AGN, that reflects the SCD of the AGN, that in the U band, this particular AGN is at about magnitude 19.2. In the R band, somewhere between 18.9 and so on. So that is why the normalization of the light curves is different. So that is reflecting the SCD of the AGN. And then the individual data points that you can see here, these are then the forced photometry PSF fluxes from the pipelines that we get. And the sampling of the data points follows the cadence that we are simulating. So this is the baseline version of 4.0. So that especially in Cosmos, you have these periods of gaps. I think it's about it should be about 6 months of non-observations. But that is basically the sampling that you get. That you have almost nightly visits, and then you have nothing, and then you again nightly visits. And this is from the baseline version of 4.0 that we are simulating. And in this particular example, a lot of the data points are actually flagged, and I'm doing quality cuts in this notebook, saying that okay, I want only high quality observation for this particular source. This is the object ID of this particular AGN. It just happens that many of the data points are flagged. If I move on to another source, so this is another object from the object table, you can see that the density of the points is much more. And something to keep an eye out is that there will be things that go wrong for various reasons. You observe at Hermas 2, for example. You seeing is 2 arc seconds, or so there are things that are going wrong. This is this is part of it is accuracy of the simulation that we have, so that we are simulating all of these systematic effects. But the downside is that we are going to have things that are going wrong in a way that requires investigation. So, for example, if you see one PSF flux 100 sigma away from the light curve, there could be multiple reasons for that. One thing that we actually investigated was that sometimes you have a photometric calibration with a low number of PSF stars. Photometric calibration is bogus, so any flux measurement from that particular visit is also bogus, and these kind of outliers show up very clearly if you look at the forced photometry and especially the light curve. So if you have one night of bad observations, you're going to have basically all the data points outside of what you would like to measure.
Okay, somehow.
Do we have track of that?
Yeah. So
well, it's 330 million rows of data. So it's a work in progress. So you have quality flags for the PSF flux. You can look at the altitude of observations, or then you can look at the seeing. But the exact cuts that you should make is we don't know yet. And it's in this particular demo, I was exploring it a little bit, trying to let's say do sigma clipping. So we select on only the good quality observations. We put a signal to noise ratio cut. We try to do sigma clipping and see if we get something useful out of it. So,
but you should, whatever is affecting your photometry, it's produced by the pipeline. So there should be track somewhere.
Yes.
That something went wrong. So in principle,
yes.
You could recover. Then maybe in real life,
that's
possible, but in the simulation, yes. Right.
No, exactly. Everything is trackable, but there are so many pathways to take that it's not clear what to do. for example, it could be a combination of air mass and seeing that gives you bad photometric calibration. And then what exactly is the the cut that you want to do in the data is it needs to be investigated. But in principle, everything is trackable. We know each individual CCD, where it was on the sky, at which modified Julian date. And we don't have storms in our simulation, but in principle, if there was a storm one night, we could discard that data point.
This is extremely important because let's see, clusters, ETF, the outliers are all over the place. And if you're not careful when you clip them, you throw away the AGN variability signals. So knowing what kinds of things will go wrong or what's a good filter to apply is super important.
Yes.
So you have the real light curve, and then so if you want to find out what you missed, is that possible using the current software? Let's say that's the one you generated, but I want to see the real one for the real AGN before the clouds and everything.
Well, what is the real AGN? What do you mean? The
intrinsic light curve.
It is here in the plot.
In the plot. Okay.
Yes.
So I can get
so the lines the lines here are the light curves of each band.
No, but I think it's a good suggestion because we can actually do it backwards. Like knowing the true light curve and the observed light curve, we can understand what combination of parameters, seeing and whatever, give us the outliers.
Yes. Yes, and I definitely agree that this should be. I mean, it should be investigated, and it should be. Go deep with this issue. And also, we have the force photometry for the galaxies, for example, which are hopefully constant in time. So that's because I think one thing that we realized when trying to play around with this variability issue was that the errors are usually underestimated. So if you just ask, okay, anything is variable which has some not likely probability, then you're going to select a lot of galaxies, a lot of stars, because typically the errors are underestimated. Okay, so this is just a repetition of, but you can see that even if we know the truth, there are going to be points that jump around while the majority of the ensemble is on the line, and it requires a little bit of detective work to go back to this observation and see why exactly is it expected and what is going on.
Can I ask about the model? I mean, I can see you're using the same model for all of those because they're not. I mean, that's all the same stochastic noise, right? So
yes.
I guess my concern is that the DRW isn't going to capture the changes in variability as a function of mass and accretion rate.
So we have the DRW model that we're using is a function of black hole mass, rest frame wavelength, and luminosity. So while you can see that the phases align, there are subtle differences between the different bands here.
B, which is 2 free parameters, you're not going to capture it. Right?
Yeah, so, it's not perfect.
So I guess my suggestion would be this. I mean, this is completely redoing everything, but maybe for a year from now or something, right? It would be nice if you could assign low Eddington variability to low Eddington sources and high Eddington variability to high Eddington sources, but then also the opposite, because I'm making some assumption that I know what low Eddington variability looks like, but it would be good to assign high Eddington variability to a low Eddington source to make sure that we could find such objects in the universe and then know that those don't exist.
Mm-hmm.
Right, but that would involve something like a DHO and at least more than 2 free parameters, right? And then kind of randomly assigning variability to go with objects.
Mm-hmm. This, I mean, one idea that I had going forward is to try to downscale it a little bit. So, for example, if we could be able to just simulate cutouts of AGN, then it would be simpler to change the underlying light curve model and then just simulate 10,000 cutouts and see what is the effect. So that would be one way of changing something very early on in the pipeline and then trying to propagate the differences.
Because in that case, we will need to test different models, right? Addressing specific cases. Because here, we just put an average dependence, just to test how I was working. But then you can have your idea what you want to look to. So they cannot run everything for every model, but if they find a way to run just the part that it's changed, then we can test more.
Yes.
I think, in fact, the message that, is we have two products. One is the DR1, which is what we are releasing. Then there is Agile, it's a software. This is an in-kind contribution. So this is something we will release to Rubin. So with the software, of course, we can do many things and we can adjust it to specific projects. If you want to look specifically to something, we can work on that.
And so if someone says, I have 1 million CPU hours, can I run your software on that?
I mean, we have the CPU now, I think, but we need person power, we need, it's still not easy, but it's something we can discuss. If there are projects that want to use the software, we can discuss and, decide where to go.
It's out of the all components that we have is not everything is computational expensive. The truth catalogs we basically run with the laptops, and then the image simulation is I thought that the raw image simulation would be the most computational expensive part, but it's actually the forced photometry, and we didn't even perform the forced photometry on difference image analysis objects. So that was actually the bottleneck at the end of the day. But yeah, different parts of the software give you different hardware requirements. Okay, so let me still I don't want to take too much time, but this is so this was from what I showed yesterday, the notebook comparing our data release 1 and the data preview 1. So we selected observation from the data preview 1 from the ECDFS. Let me see if this is
A bit through also how to do things.
How to do things.
Yeah,
Yes. Okay, so the gist of thing is that okay, here I'm defining 2 Python functions, but the gist of the things is that because we are so close with the data model, we can basically do the same thing with Agile that we can do with the data preview 1. We just have a different way of accessing the data, because with Agile we have the master database, and then with the data preview 1 in this notebook I'm actually using the API. So I'm using this notebook to actually interact with the Rubin database. So the way you get the data is a little bit different, but then once you have the data is basically the same. So in this notebook in particular, many of the things that we are doing with Agile, we are just directly doing them with DP1. And I thought this was, for me, this was the point that all started to come together, that we actually can easily compare our simulation with the observations. So as an example, this is just the number of visits that we have in the 2 tables, but the cool thing is that it's just basically it's just a simple for loop over the 2 different tables, which are of the same data model. So we can do the same things with the 2 tables. So this is all the so I apologize for the label. This is all the visits in the DP1 compared to Agile data release 1. So if we just select the extended channel rebuild south, we have about 2 times more visits compared to the data preview 1 in the extended channel rebuild south. So we got it running, but with the first data release we don't have it at the moment. It's still possible for us to run it. I mean, we just stopped processing after the forced photometry part, and basically we did not fully know how useful the DIA objects are for AGN science, and this is something that I think we should look into data preview 1. And I had this chat with Maurizio that for low luminosity AGN, removing the galaxy from the image having a template for the galaxy that gets removed from the image would allow you to recover better the underlying low luminosity source. Yes.
And I think the position of the observatory is that the photometry and the difference images is the photometry to use because it's exactly less sensitive to overcrowding and photometry issues. And when you look at the light curves or what we would say structure function, variability, you can see that it is less, it's better. It's still, especially for things brighter than 20, it's still variability is much larger than photometric errors, but it is better on the difference images. If you take, a PSF on the difference image add template, it's better than the direct image process.
Okay, that's very useful to know. I think definitely we should then finish the pipelines for the IA objects.
Not BIA, it's premise with BIA object. It's also for normal objects, but I gives you two photometries.
Sure.
The correct one and the one on the difference.
Sure.
Photometry on the difference images should be performing better. It does perform better.
And this is already in the forced photometry tables, no?
Yes, it's all in the forced photometry.
Okay.
Yes.
Phew. So then we don't need to do anything. No, okay.
Like two measurements done in the forced photometry table. One is on the direct and one is on the difference.
Yes.
Yeah.
So you've made the difference images, you just haven't done the detection of the difference images.
Yeah, exactly.
Yeah.
Oh, okay.
Yeah.
I just forward you a session 2018 slide.
Oh no.
I'm curious to have you take a look at it. One question of how you actually construct a light.
Okay, I will just go briefly through the rest of this notebook. So what we are doing here is that we're loading the AGILE object table. We are loading the DP1 object table in the extended genetic field south. Let me show you it's just a collection of columns, all the measurements that we want in the UGRIZY bands, coordinates, extendedness, something that we can play around with in the rest of the notebook. The sky positions, I mentioned this yesterday. So we have bright stars which are masking some of the detections, but we also have regions of high density of galaxies. And with the LST science pipelines, this is something that is skipped. It's deemed too complex to deep blend, and we did the calculation that it could be some up to 15% of galaxies that are skipped this way, which is something that we are also investigating. And if we end up fixing it easily, then we will fix it. But the bottom line is that the area is not exactly the footprint of the survey, and this is true for any survey. So this is if somebody does statistical analysis with these masked regions need to be taken into account, otherwise the area will not be correct. And yeah, as per yesterday, it's the same with the official data release with the science pipelines that if you go to the most crowded region in the universe, the science pipelines will just say, okay, I will not deep blend this, and then you will not have objects, for example, in the 47 Tucana. So this is looking at the magnitude distribution of the two different surveys. So it's the extended and point-like magnitudes. This is in the R band, and then R simulation is in the blue, and then the DP1 is in the orange. And here the normalization is not 1-to-1 because we did not do the area calculation of either one of those. If you want to get the counts as a function of area, the magnitude at the magnitude limit of the survey, you need to be really careful to be doing the incompleteness correctly. But here you can see beautifully, for example, that you go to a faint magnitude here at about 24. You are no longer being able to distinguish very well between galaxies and non-galaxies. So basically, you can see that at fainter magnitudes, you can see the jump in the histogram of the point-like sources, because that's when the galaxies are entering the selection. So at bright magnitudes and point-like sources, you are still able to distinguish between stars, galaxies, and AGN. Typical stuff. we did a calculation of the signal to noise ratio. So in AGILE DR1, this is signal to noise ratio on the y-axis. This is magnitude on the x-axis. So in AGILE DR1, we are a little bit, we are, let's say, more optimistic and more homogeneous than what they have in the DP1. So this in the extended scientific deep field south, you have of course non-uniform observations. So towards the edges of the survey or the edges of the commissioning camera area, you have less exposure time. So that's why you get non-uniformities in the a higher scatter in the signal to noise ratio. We also put the numbers in, so just interpolating the previous. So for the PSF flux, looking at signal to noise ratio 3, 5, 10, and the magnitude limit of the 6 different bands in AGILE and data preview 1 in the ECDFS. And the final part of this particular notebook was to look at the color distribution. Basically, we wanted to do this to see where do we stand. Where do we stand? Are we able to do a good job at basically reproducing the observations? And of course, the observations are not perfect either. So this should be taken with a little bit of a grain of salt. So for example, if we do a point-like selection in R, we do a R magnitude cut. This is the bright magnitude cut. So basically, you see the main sequence of stars, and then you see the typical location for your bright and blue quasars somewhere around here. If you do this plot without the R magnitude cut, everything blows apart, obviously, because you're including a lot of galaxies, and the galaxies are basically everywhere in this plot. So for the QSO selection, doing the point-like cut and the brightness cut is the way to exclude the galaxies. So here you see the type 1 AGM basically moving towards the red in the GRRI. So it becomes more complicated to distinguish between them, but this is everything that is known. So from the point of view of AGILE, we can then go to the matches, and then we can actually put the labels on all of these different points. So we can redo the color diagrams where the positions of the sources are visible. So here you can see with this R magnitude cut of 24, we still have some galaxies that are present in the locus of the QSO. So this would be an impurity for the quasar selection. And yeah, I think I will leave it at that, not to take too much of the time, and have time for the discussion of what we want to do with the real data.
Yeah.
With-
So that's the real LSST data, right?
The orange points, yes, that's from the data preview 1, and observed colors. So
Like a lot of the. There's just a cloud above the stellar locus. It's probably WG plus M's that are not big result.
do you mean this one?
Yeah.
Yeah, I think the area is what I think you wouldn't expect this many.
Is this using all the flags that James was talking about yesterday?
I did not follow the session, but I think I'm using the quality flags in the PSF flags and the extendedness flags. So the philosophy for me was always, if I use the flags, if I use the extendedness, I keep the flags. So I'm not sure. I'm not sure which flags should be added to this, but I should know.
Like the cloud on the bottom right corner, right? Is that, or those all real sources, or are they?
Probably you have also noisy measurements, because unless you do, 10 sigma, 10 SNR cut or something like that, then there's gonna be bound to be noisy measurements. So unsure. So yes, a disclaimer: I'm not a DP1 spokesperson. I did this as like on my best effort, choosing the flags that seem to make sense and choosing cuts that clean up the data a little bit. But I'm not claiming that these are the final flags that we should use.
Any other questions for Akke? Okay, well, let's give it a floor.
Thank you.